This video is brought to you by Sir Isaac Newton. Okay, we're studying mechanics. This is the first video, so I'm going to do previous exam papers, and let's start off with last year's exam paper 2024. So question 1 is a circular motion question. You should expect to have one of these. Very standard. So there's a bit that I cut out there that they don't show you on the website. So Jono and Tony are in the kitchen. Their dog is sitting on the floor next to them when the neighbour's dog comes in and playfully chases it around the table. How is the neighbour's dog getting in there? Okay. So the dog runs in a circle. So the very smart dog, it knows what a circle is. Add a labelled arrow to the diagram to show the force acting on the dog as it runs in a circle at a constant speed. Well, there's a centripetal force which is always towards the middle, the centre of the circle, and I guess the dog is going pushing that way as well, although you don't really need that one. But I think this is the one that they're after. They're after that force right there. So far, so good. The first real question is this one here. So the mass of the dog is 10 kilograms, so it's already in our SI units, which is good. So 10 kilograms, so M is 10. The dog is moving at 0.87 meters per second, which I guess is the speed that he's going around the circle. So that's our velocity, is 0.87. And it tells us that the centripetal force is 15 newtons. So it's already in SI units for us. So the centripetal force is 15. Okay, calculate the radius of the dog's path. So for this one, we're going to use the formula that's given. FC equals what is mv squared over r. Okay, we know m, we know v, we know FC, and we're looking for r. So now it's really not a physics problem, it's an algebra problem. So 15 is going to be equal to 10 times 0.87 squared divided by r. So if we rearrange that, we can swap the 15 and the r. R is going to be equal to 10 times 0.87 squared divided by 15. And we're just going to grab our calculator and do it. So 10 times 0.87 squared equals that, divided by 15 is that, so 0.5046. So how accurate do we need it? Well, the 10 kg there is 2 significant figures. This is in 2 significant figures. This is in 2 significant figures. So let's do this one in 2 significant figures. So 0.50 meters, which is 50 centimeters. So the dog, this horrible yapping mutt, is running around a circle with a radius of 0.5 meter. How did the dog get it? Okay. So perhaps I should maybe do a little bit of an explanation about what's happening here in this diagram. So in order for this dog to be going in a circle, it is sort of pushing itself that way, and I guess the ground is pushing back. But in order to keep it as a circle, there has to be a force towards the middle. So when the dog is here, the force is still going to be towards the middle, but the dog's going to be kind of facing that way. So this kind of force vector, I guess you could say, it's not really of the dog going that way, is sort of offset by the force towards the center, and that's what keeps it in the middle. If you think of your car, when you turn a corner, what's pushing towards the center? Well, the friction of your tires on the ground. So you'll turn your tire to go that way, so there is a force pushing it towards the center of a theoretical circle, and your car is going to turn like that. So this is the force that they want you to show, and that's the centripetal force. So next question, on the other side of the table, the dog hits a slippery patch. So we have our rather happy looking dog here, and it slides off at a tangent. Use physics principles to explain the dog's velocity immediately after it starts moving off on a tangent. So the direction it's going to go in a straight line that way. And why is it doing that? Well, it's doing that because of Newton's first law. Okay, so that law says that an object in motion will stay in motion at the same velocity, speed and direction in the same direction unless acted upon by an external force. So that's really terrible. Let's rewrite that. So Newton's first law. Okay, there is no centripetal force anymore. So this force is gone now as soon as it hits that slippery patch, and the only thing that's kind of acting on the dog now, well, there's nothing acting on the dog now. It's just going to go and slide there in a straight line. That's the long and short of it. We're going to presume that the slippery patch, so the friction disappears. So the centripetal force is going to equal 0. So the velocity of the dog, this mutt that's run into our house, is going to be the same velocity, so 0.87 meters per second in this direction here, until, I guess, friction stops it. The net force is going to equal 0 as long as there's no friction, and because you never have no friction. But as long as it's on this slippery thing, whatever it is, this mutt is going to fly off there at a tangent. Alright, the next question says that the dog slides along the floor towards Jono. So even though it isn't his dog, Jono reaches down and cushions the dog as it slides into him by putting out his arms and then gradually bringing them towards him. Okay, the dog takes 2 seconds to come to a rest unharmed. So even though this dog has come into your house and is chasing your dog around, perhaps, giving it PTSD, canine PTSD for you still save the dog. So, okay. So Jono uses physics principles. So use physics principles to explain why Jono put his arms out to cushion the dog rather than let the dog stop quickly in 0.1 seconds. I mean, if it had been me, maybe a bit different. Actually, I probably would have saved a dog. start by calculating the force experienced by the dog. So the keyword here is the force experienced by the dog and the collision. So this is an impulse. This is an impulse momentum problem, really. Okay, so impulse momentum, kinetic energy, force, they're related. So I'll do a video on that a bit later on. We're really interested in this sort of stopping force, the amount of force that you have to exert on this dog in order to slow it down. So impulse is the change in momentum given a change in time, and it's given to you in the exam in the form of, in the formula, it's given to you, F change in T. Okay, so we want to find this force, and we know the time. So there's going to be 2 times that we're going to do, 0.1 seconds and 2.0 seconds. So obviously, if you stop suddenly in 0.1 seconds, as opposed to slow down gradually over 2 seconds, you should kind of intuitively know that the dog is going to have a much nicer experience if it stops slowly than if it hits a wall. All right, so we need to work out a few things, don't we? So the momentum, and it's P. We use P because obviously M is mass. The momentum is equal to the mass times the velocity. All right. We want to measure the change in the dog's momentum. So it's a bit like that old saying that it's not, if you jump off a cliff, it's not the fall that kills you, it's the landing that kills you. So we need to work out the initial velocity and the final velocity in order to do that. So the initial velocity, so VI, is given at 0.87 meters per second. We worked that out in the last question, and the final velocity is going to be 0. You're going to bring the dog to a stop. Now the dog, we're told, is 10 kg, so that's the mass. So our initial momentum is going to be 10 kg times 0.87, which is 8.7. Momentum is in kilogram meters per second, isn't it? Yeah. It doesn't have a name of a unit, by the way. Sometimes it's called a Galilei, I've heard, but not in this case. So the change in momentum is going to be the final velocity times the mass minus the initial velocity times the mass, and the mass doesn't change. So change of mass given a change in time is 0. The dog is not moving close to the speed of light. It's not gaining mass or energy or anything. But the final velocity is 0, so that disappears. So the change in momentum is going to be negative 8.7, what did we say, kilogram meters per second. So the negative bit means it's a sort of force opposing where you're going, because momentum is going to be a vector. It's going to have a direction as well as a magnitude. All right, so given that we know that, let's sort of rearrange our formula that we've got. And we know this one now, and we know this one, and now we can work this one out. So we're going to rearrange it so that the force that the dog feels is going to be equal to the change in momentum over the change in time. Now notice here that the force is going to be greater as the time gets smaller, because as we divide by a smaller and smaller number, the force that the dog feels must be bigger and bigger. So you kind of intuitively know how this works. We're going to do a lot of force really quickly versus the same force over a longer period of time. One of them is going to be not as unpleasant as the other. Okay, so we know that the change in momentum is going to be 8.7. So the force that the dog feels in, say, 2.0 seconds is going to be 0.87. It's already in SI units, divided by 2. And that's going to be some number. It's going to be some number. And we're going to work it out on our calculator. So there's going to be some number, and we're going to work it out on our calculator. So negative 8.7 divided by 2, negative 4.35. Negative 4.35 what? Well, it's a force, so it's a Newton. So it's a force opposing the way that we're looking, 4.35 newtons. Okay. It wouldn't be great, but okay. So now let's look at the force that the dog has if the time was 0.1 seconds. So this is going to be 0.87 divided by 0.1. And that's going to be much greater. So the force that the dog is going to feel now is going to be minus 8.7 divided by 0.1, 87 newtons. So 87 newtons in the opposite direction of where we're going. So it's going to feel a lot more of a whack here than here. All right. So yeah, I think maybe we'll do some further questions on that, and I'll do probably a couple of videos on impulse, because it is quite an important topic. A question that often comes up in the exam is why do cars have crumple zones? And the reason cars have crumple zones is that the change in momentum is spread out over a bigger period of time. So if a car has a crumple zone, which is kind of a void and an empty space at the front of the car, if it hits an object, it will take time for it to sort of crumple up. So this does two things. So it increases the time, and also the energy is absorbed and sort of re-vectored around the people in the car. Maybe we'll even, I'll show you what I mean by that. So we're looking down on the car. So the car hits a wall. So the car's going that way, and it hits this wall. So it gets pushed back into the crumple zone here. So the time that it's in contact with the wall increases. So the change in momentum and the impulse is spread out over a longer period of time. So there isn't as much force being transferred into the car. And also this absorbs energy in the form of heat, sound, can disintegrate. They're designed to disintegrate, and also the force is channeled away from the people in the car. If we hit a wall, okay, it's not great, but we want the car to absorb the change in momentum and the force, and not the people in the car and their dog, I guess. So the next question is a collision question, sticking on the theme of dogs, and there is a rather, I guess the Photoshop budget wasn't that great. No, doing this exam, there's just this one cut and pasted and sort of rotated around. So Jono releases his 10 kg dog. Is it his dog? I thought it was the neighbour's. Oh. And it runs directly towards the neighbour's dog at 1.1 meters per second. So it's 10 kg, 1.1 meters per second. The neighbour's dog, mass 12 kg. That's quite big. That's way bigger than this dog. So it's not even really representative. Okay. Runs towards Jono's dog. They collide, stick together, and slide across the floor at 30 meters per second, 0.3 meters per second in that direction there. Calculate the speed of the neighbour's dog as it was moving before the collision. So let's pluck out what we know here. So the mass, this is the mass, let's say mass 1. This is mass 2. The direction is that. We don't know this velocity and we need to find it. And this one has a velocity going that way of 1.1 meters per second. And the final sort of mass is going to be these two added together, which is going to be 10 plus 12. So it's going to be 22 kg. So the two dogs together is going to have the same momentum as the two dogs separately. You can't destroy momentum in an inelastic collision. This is an inelastic collision because the dogs stick together. They were very careful with the way that they set it. They collide and they stick together. If it was an elastic collision, different rules would apply. So let's work out the momentum before and the momentum after. So the momentum before is going to be mass 2 times the velocity, which is what we want to find in that direction, plus the mass of this dog here times the velocity of that dog there. But it's going in this direction, so it's going to be a minus sign. So let's work it out. So it's going to be 12 kg times the velocity minus 10 kg times 1.1. Okay, kind of in that direction. And this one here is also going to be in this direction. So it's going to be the final momentum is going to be 22 kg times 0.3 meters per second, also in that direction. So now we can find out what the velocity of this dog was. So let's work out the final velocity, the final momentum first, because it's going to be the same as when we began. So that's going to be 22 times 0.3. So 6.6, whatever it is, in that direction. So now we know that 12 kg times V minus 10 kg times 1.1 meters per second must equal 6.6. So now it's no longer a physics problem, it's an algebra problem. So this is going to be pretty easy to do. We're just going to multiply it by 10, so it's going to be 10.1. No, it's going to be 11, isn't it? Yes. So 12 times the velocity minus 11 equals 6.6. And how are we going to do this one? So 12 times the velocity must be equal to 6.6 plus 11. So 12 times the velocity of the first dog, let's say V1, is, what's that going to be, 17.7. So the velocity of the first dog is going to be 17.7 divided by 12. And let's grab our calculator and work that out. .475 meters per second. So that's how fast that dog was going before it started. Oops, and I see I've actually made a mistake. I thought I got that wrong. So it's 17.6, because 6.6 plus 11 is 17.6. So 17.6 divided by 12. 10.6 divided by 12 is 1.4666 recurring. So I guess they want it as two significant figures, so let's say 1.5 meters per second. Okay, now question 2. Tony decides to make a cake. So he's had enough of the dogs, so hopefully he washed his hands. Tony and Jono measure 0.11 kg of flour. Okay, so that's going to be our mass by the looks of it. Of flour using a kitchen balance as shown below. And they don't actually show it, it's copyrighted or something. There are 3 springs in the balance. Each gets compressed 0.01 meters, so 1 centimeter, when the flour is added. The simplified diagram shows the springs in the balance. Add labels to the diagram above right with the flour to show the 2 forces acting on the flour. Okay, well, the first one is going to be the force from gravity, and the second one is going to be kind of the not really good direction. It should be pointing straight up, and that's going to be the normal force. And they're going to be equal. Equal in magnitude, but in opposite direction, because the flour is not moving. If it's moving, it's in equilibrium. Fair enough. All right. Calculate the spring constant for one spring. Okay, so we're going to presume a couple of things. We're going to presume that each of these springs is the same. So there's 3 springs, and they're each going to need to push back some force. So first thing we need to do is we need to work out what this force due to gravity is, and that's going to be mg. And so that's going to be, what did we say the mass was? 0.11 kg. Times gravity, and they want us to say that gravity is 9.8 meters per second. Okay, and time to grab the calculator. So 0.11 times 9.8 is 1.078. newtons. Okay, so that's the total force going down, but it's distributed between these three springs. We're presuming again that each of these springs is taking equal amount of the weight. So the force on one spring is going to be 1.078 divided by 3. So let's divide that by 3. And we get 0.3593333. Fair enough. Okay, so now we know what the force pushing against the spring is, and because it's in equilibrium, the force that the spring is pushing back must be equal to that. So we know using Hooke's law that the force that the spring is giving us must be equal to kx, where x is the displacement from the weight. And we know what that is. It's given to us at 0.01 meters, so 1 centimeter. So this Fs must be the same but opposite in direction as that. So now it's an algebra question, not a physics question really. We want to find K. We've got that. Okay, so 0.3593333 is going to be equal to K times 0.01. So K is going to be equal to the 0.359333333 divided by 0.01. And you don't really need the calculator for that. We're just going to move the decimal place 2 places. So it's going to be 35.9333333 Newton meters. Newton per meter, I think. Yes, would be Newton per meter. And we want two significant figures, so we're going to say that's approximately 36 Newton meters. And we're done. So the K, one spring, whoops, helps if you can see it, isn't it? So the K on one spring is going to be 36 Newton per meters. Maybe if you couldn't see it, so we divided that by that, we got that, and then we rounded that to two significant figures. Maybe put that in brackets. Okay, now Jono brings the groceries to the front door, and now we see how this damn dog got in the first place. This guy just leaves his front door wide open. Any dog, any axe-wielding maniac could just walk on in. In fact, he even gives them a ramp. So an axe-wielding maniac with mobility issues could even get in. Now we see. All right. He's found it takes less time to go up the ramp than the stairs. All right. Compare both routes by considering work done, force required, and the power. Okay. So the work done, the work in this case is just going to be the work raising the groceries this vertical distance. Okay, so the work done regardless of your path, it's I think it's a conservative force, I think, is the mass times gravity times the height that you raised it. Well, the height is the same, gravity doesn't change, and the mass is the same, so the work is going to be the same. They don't give us any numbers, so they just want us to comment on it. Okay, the force required. The force required, it says that it takes less time to go up the ramp than the stairs. It's the same amount, but the ramp is going to trade off. How can I put it? You're going to do the same work but over a longer distance. So the force required is going to be less on the ramp. So you do that same work in that much longer distance. You're using less force so you can get up there quickly. It is technically, I think it's called, it's technically a simple machine, and that it's designed to lower work rate. All right, power. So the power is going to be greater on the ramp. And the reason we say that is that power, let's look at the equation. So power is the work done divided by the time it takes you to do that work. All right, we know that the work is the same, but we know that the time for the ramp is less than the time for the stairs. Okay, so therefore, let's say the time here is 10 seconds and the time to go up the stairs is 12 seconds. Well, the same weight divided by 10 is going to be greater than that same weight divided by 12. 1 over 10 is greater than 1 over 12 for any of those. So our power, the power in the ramp is going to be greater than the power required to get up the stairs. Simply because you're doing more work in less time. You're doing the same work in less time, which is the definition of power as far as physics goes. All right, well, Tony, it's Tony's turn now. Tony's using a spice rack by hanging wires from above the workbench. Okay, as shown below, the ginger spice kilograms, the salt 0.5 kilograms. The uniform rack has a mass of 0.37 kilograms and is 0.4 meters long. The ginger spice placed 1.5 meters, 0.15 meters, and the salt is placed 0.5 meters. So I guess that's there and this is there. From the left hand side as shown above, the maximum tension force that each wire can provide is 10 newtons. Okay. State the conditions required for the spice rack to be in equilibrium. Okay, well, there's two things that are required for it to be in equilibrium. First thing is that all the forces going down from gravity must equal all of the forces going up. Otherwise, this thing would plunge to the ground, or if the normal force was greater than the gravitational force, it would be kind of floating away. It's not, it's staying right where it is. So that must be the first condition. So forces going up must be equal to the forces going down. Okay, next thing is that the torques going clockwise must be equal to the torques going anti-clockwise. So there's going to be like a fulcrum here, and it's going to want to go that way. And here there is a fulcrum at the wire, and it's going to be wanting to go that way. They must be the same, because obviously this thing's not moving and it's not twisting around. So these are the two conditions. Okay, so given that, now they want us to perform suitable calculations and decide if the wires can hold the spice rack with the ginger and the bag of salt. Okay, well, we're going to use what we knew from above, so the forces up must be equal to the forces going down, and the torques that way must be equal to the torques going that way. Okay, so let's look at the weight of the everything that's pulling down. So the weights that are given is 0.03 kilograms and 0.5 kilograms, and the rack itself has a mass of 0.37 kilograms. Okay, so the weight of the salt, remember weight is mass times gravity, otherwise known as force from gravity, is mg, and m, the mass of the salt, is equal to, and I'm doing these separately because they're in different places, and this is going to help us when we do the torque, 0.5 kilograms, so it's already in SI units, and gravity is going to be 9.8 Newton meters, and so therefore the force of gravity of the salt is going to be 0.5 times 9.8, which is going to be 4.9 newtons that way. Now we want the, so this is the salt. Now we want the, what was the other one? The ginger. Okay, the ginger. So the force of gravity of the ginger is going to be, what was it, 0.030 times 9.8. We're going to presume that the gravity is the same. So that's going to be 0.03 times 9.8. 0.03 times 9.8, which is 0.294. Newtons. And then the rack itself. So the force of gravity on the rack is going to be the mass of the rack, and the rack was 0.37 kg times 9.8 newtons. And again, we're going to use our calculator. 3.626 newtons. Fair enough. So that's the weight. Now we want to calculate the tension on is that going to be too much? Okay, so what I've done here, I've sort of redrawn this so we can actually see this. So the salt, let's work out the torques now. So let's use this left-hand side torque as our left-hand wire as our fulcrum point. So from here we're told that this distance here is 0.05 meters, and this distance from here to there for the ginger, we're told that this is 0.15 meters. That's a wonky meters. And then we have the force from the rack, and that's going to be halfway between them. We're going to take it from the center of mass. it tells us it's a uniform rack, so we're allowed to do that. And that distance is it's 40 centimeters across, so this is going to be 0.2 meters. Okay, so the torques going that way, using this as our fulcrum point, is going to be the force from the salt, which we worked out, 4.9, times that distance, 0.05, plus the torque from the ginger, which we worked out as 0.294, times that distance, which is 0.15 meters, plus the distance, the force from the rack itself, which is 3.626 newtons, times 0.2 meters. And we're going to get some force from that. So this is going to be, how are we going to get this one out? So let's just put it in straight away. So 4.9 times 0.05 plus 0.294 times 0.15 plus brackets 3.626 times 0.2. Remember, it has to be in meters. We can't use centimeters. It has to be in meters if we're using SI units. So that's going to be 1.0143. So what does that tell us? That tells us how much torque has been put onto this cable here. How much is this pulling down? So that torque is going to be the number that we got just before. The 1.0143 business times 0.4 divided by 0.4, and that's going to give us an answer of 2.53 newtons, which is less than 5 newtons, so this one is okay. Okay, now that we've done that, now we can calculate the force on the left hand side. So using this as our fulcrum now. I think we'll do some videos. If you're having trouble keeping up, you can fast forward a wee bit. So the sum of the upward forces must be the sum of the downward forces. So the downward forces on each is going to be the same as the torque. So the torque on this left one plus the torque on the right hand side has to be equal to the force being pushed down from the salt plus the force being pushed down from the ginger plus the force from the rack itself. Okay. We know the force on the right hand side. We work that out as that. Now we need to find the torque on the left hand side using that. So the torque on the left hand side plus 2.53 must be equal to the force that we had, which is 4.9, plus 0.294 for the ginger, plus the force from the rack itself, 3.626. Okay. So TL, the torque on the left must be equal to 4.9 plus 0.294 plus 3.626 minus 2.53. And that's going to give us a number. So let's work it out. And I think this is going to be our moment of truth, because we know that the right hand fulcrum can take it, but our left one here, just looking at it, is taking a lot of the load. So if either of them is going to break, it's going to be this one, and I think it's going to break. So they can take 5 newtons. So 4.9 newtons plus 0.294 newtons plus 3.626 newtons minus the force that the other tension, the other cable is taking, is that, and it's 6.29. So the torque is 6.29 newtons, and that is more than 5 newtons. So the left hand side wire will break. It can only take 5 newtons, and we're wanting it to carry 6.3 newtons, 6.29 newtons. It's not going to do it. It's going to snap. Hopefully the dog gets out of the way. Last question. Now we're told that our pair of dog-loving bakers are wanting to add apples to the cake. Okay. His friend, so Tony is adding apples. His friend Jono rolls an apple along the table. The table leaves his hand at that velocity there, 0.56 meters per second, and stops in front of Tony. It takes 4 seconds to roll along the tabletop. So obviously this must be a round apple. Okay. Nice green apple. Calculate the acceleration of the apple. Okay, we want to turn this into an algebra question, and we're going to use the formula final velocity is the initial velocity plus the acceleration times the time. The time we know is going to be 4 seconds. The final velocity is going to be 0 because it stops, and the initial velocity is this 0.56. Now straight away we should know that our acceleration is going to be a negative number, because it slows down. It starts at some number and it slows down, and we're going to presume that it slows down in a uniform manner. So let's put in the numbers and see what we get. So final velocity is 0. Our initial velocity is 0.56 plus the acceleration, we don't know, but we know that the time is 4, so it's going to be 4t. So that means that t, if we rearrange that, is going to be negative 0.56 divided by 4. So negative 0.56 divided by 4 is that negative 0.14. Negative 0.14. If you don't have the negative, you would get it wrong. The negative must be there because you're slowing down, not speeding up. If the acceleration was 0.14, it would get faster and faster. Okay. Tony now throws the apple to Jono. Okay, this is getting serious. The angle of the throw is 40 degrees and the initial velocity is 5 meters per second, as shown in the diagram below. Okay. Calculate the vertical and horizontal components of the initial velocity. So we're going to do a velocity triangle. So it's going to be a right angle triangle. The apple is moving at 5 meters per second in that direction at an angle of 40 degrees. Okay, the vertical velocity is going to be there. The horizontal velocity is going to be there. So how do we do that? Well, we've got a right angle triangle. We're going to use trigonometry. We're just going to use our sine, cos, and tan. So our vertical velocity, that is the velocity going in that direction, is the opposite. So it's going to be sine of 40 degrees times the hypotenuse, which is 5. And we grab our calculator and we make sure that it is in degree mode. It cannot be in radians if they give it to us in 40 degrees. So sine of 40 times 5 is 3.21 meters per second. They give it to us 0.56 meters per second before, so I'm going to do it to 2 dp. Okay, the horizontal velocity is the adjacent side, so it's going to be cosine of 40 degrees times 5. So cosine of 40 degrees is that times 5 is 3.83 meters per second. Okay, so this apple, it's moving in that direction at a velocity of 3.21 meters per second, and it's moving along the table, the ground speed, if you will, of 3.83 meters per second. Right, next question. So we have the apple here, quite fitting for Newton. So they've sort of reversed the direction though. So identify the type of motion. Well, it's going to be projectile motion. I'm not quite sure why there's 3 lines there. So projectile motion just means that all of the forces at the beginning apart from gravity, I guess, and nothing is propelling the apple. Okay, so after he throws the apple, it doesn't suddenly get, rocket powered apple. Nothing of that happens. It just goes up, gravity pulls it down, and it lands in a nice parabolic arc. Okay, so now they want us to describe the points. So they want the forces, if any, acting on the apple, and the direction of the velocity of the apple. So I guess we need to remove these rocket engines. So the forces that are acting on the apple, well, once a projectile, the only thing acting on it is the force from gravity. That's it. There's no other forces. You fire it off and let it go. The direction of the velocity, you could do this one of 2 ways. You could decompose it as the vertical and the horizontal, but I'm just going to give the net velocity. So that's going to be our initial velocity. That's going to be our velocity at the top, and that's going to be the velocity at the end. It's always going to be a tangent because of Newton's first law. Okay. Describe how the vertical velocity and the horizontal velocity of the apple change throughout its flight. Well, the horizontal velocity. So if you're looking at this from above, the apple would sort of start there and it would just go across. So you're looking down, say you're a fly on the ceiling. The apple is just going to go at a constant velocity. Okay, if you're looking from behind, so the vertical velocity, if you're looking at it from behind, you're going to see the apple go up it'll slow down and stop and then come back down again. So it'll be that, then nothing, and then down. I think that's it. And I bet this is what they want us to work out in the next question. So let's go to the next question. And now we have the projectile motion final. So the setup is that the ceiling is 1.5 meters above the surface of the table. Calculate the maximum height reached by the apple as well as the horizontal distance covered and determine whether the apple will reach Tony 2 meters away. Okay, so in other words, if this is the tabletop and you throw it from the top of the tabletop, I don't know why, if he's 2 meters away, and it's going to go up at an initial angle of 40 degrees. It's going to go up in a parabola and it's going to come down and land. And we want to know whether this distance here, first off, we want to know whether this distance here is greater than or less than 2 meters. And we want to know whether this distance here is greater than or less than 1.5 meters. Okay. So how are we going to do that? Well, if you remember, we worked out the velocity along the ground. So the thing we need to do first is deal with the vertical velocity, because that's going to be more complicated. So the vertical velocity, when we started, we worked it out as 3.21 meters per second. Starting from here, going in that direction. So what is the acceleration? The acceleration is going to be from gravity, and it's going to be negative 9.8 meters per second. Okay. Now, at the top here, we're going to, it's going to stop. So the velocity, the upwards velocity at the top is going to be 0. So let's work it out. The final velocity is the initial velocity plus the acceleration times time. The final velocity at the top is going to be 0. The initial velocity is going to be 3.21, and the acceleration is going to be 9.8 meters per second. Now we can solve for time. So 0 is going to be equal to 3.21 minus 9.8 t. Solving for time. So we're going to bring this 3.2 over. So the time is going to be equal to 3.21 divided by 9.8. They're both going to be negative, but they're going to cancel, I guess. So 3.21 divided by 9.8. Is 0.33 seconds. So that's the time it takes to get from there to the top. Now, the time that it takes to get to the other side is going to be twice that. We're going to presume that there's no air drag. So the time to the other side, the total time is going to be 0.66 seconds to go up and then come down again. Okay? And we know that the horizontal velocity doesn't change. And the distance is the velocity times the time. So the distance it's going to move is going to be that 3.83 meters per second times 0.66 seconds. And now we can work out how far it's going to go. So 3.83 times 0.66 is 2.5 278, so 2.5 meters. So yep, Tony is going to be about here. There's 2 meters, so you're going to have about 50 centimeters to spare. So yes, it will reach the other guy. Okay, now we want to know, will it hit the ceiling? No. So for that, we need to go to the kinematic equations. And for this, we're going to use the equation that's given in the formula. D equals VI plus VF divided by 2 times the time. Now we know the time that it takes to get from the bottom to the top is 0.33 seconds. So time is done. The final velocity at the top going up or down is 0. And the initial velocity going up is 3.21. Now we can work out the distance that it goes up. So it's going to be 3.21 divided by 2 times 0.33. Okay, and you can tell straight away this is going to be less than 1.5. So 3.21 divided by 2 is that, times 0.33, which is 0.529 meters. So 0.5 meters, which is a lot less than 1.5 meters. So yes, the other guy will catch the apple, hopefully, the same way that he caught the dog. And that's the end of that exam. We know everything we need to know about these two numbskulls. Okay.